maybe the hardest thing about this specific homework problem is reading the problem and understanding what it's telling you. So let's start reading through this problem and seeing what we can figure out as we go. So a sinusoidal wave, I've got one sketched on the screen, has a 2 centimeter vertical separation between a crest and a trough. So let's see what we mean by that. So the line that goes through the middle, that's the equilibrium. The highest points, those are the crests. The lowest points, those are the troughs. And we know in general, from the equilibrium to either peak, that's the amplitude. Okay, let's fill in what it told us. From a crest to a trough, so from here to here, that's 2 centimeters. That means it's 1 centimeter to a crest and 1 centimeter to a trough. This tells us that our amplitude is 2 centimeters divided by 2, or 1 centimeter. Okay, that's the first bit of information. From a crest to a trough has a horizontal separation of 1.25 meters. Let's put that on our picture as well. I'll just grab a different color. So from a crest to a trough, wait, I'd rather use red. From a crest to a trough, that horizontal distance, I'm just going to drop a line coming upwards, that horizontal distance is 1.25 meters. Okay, let's think about one wavelength. One wavelength is from a crest back to a crest. So our 1.25 meters from a crest to a trough is 1/2 of a wavelength. So 1/2 of lambda equals 1.25 meters. That means lambda is 2 times 1.25, or 2.50 meters. Okay, what else do we know? The wave is observed to move to the left. Let's put our wave direction on there. So there's our wave speed v, or our velocity, I suppose. Oh wait, I missed a spot. It says it takes 2.86, catch your units here, ms means milliseconds, to move from a crest to a trough. So if a distance, let's see, I'll use green this time. So for a distance to move from crest to crest, the distance it travels horizontally is 1.25 meters. The time it takes to travel that is 2.86 milliseconds, 2.86 times 10 to the minus 3 seconds. This gives us the wave speed. So wave speed is distance over time, 1.25 meters over 2.86 times 10 to the minus 3 seconds. That tells us that the speed of that wave is 437 meters per second. Okay, so we've got the wave speed. And then the last thing we have here is our initial conditions. The wave is observed to move to the left. We've got that. The initial height of the wave at x equals 0 is 0.8 centimeters, and it's moving downwards. So let's get that in our list as well. So y of 0 and 0 is equal to 0.800 centimeters. So if x is 0 and t is 0, y is 0.8. Moving downwards means that the transverse velocity, where x and t is 0, is negative. Okay, so all we've done so far is read the problem and make notes as we go. Some of these problems can be a bit tricky, so I recommend you try and follow this process whenever you can. Now we've got a huge list of information and we're ready to try and solve the problem. Now that we've really thought about the problem and we've gathered our information, let's set to solving the problem. Part A, write the equation of motion for this wave. So the equation of motion for a left traveling wave is y of x and t equals amplitude times cosine kx plus, remember we have to use plus because it travels to the left, omega t plus phi. Let's see what we have to fill in for each of these numbers. A is the amplitude. We said that was 1 centimeter. You can convert to meters if you wish, or leave in centimeters. K is the wave number. So we can calculate the wave number. K equals 2 pi over lambda. So 2 pi divided by 2.5 meters equals 2.51. X is general. Omega is the angular frequency. We know K and we know the wave speed, so we can find omega. So we know that wave speed V equals omega over K. That tells us that omega equals V times K. So omega, I need a little bit more space, is V. We said that was 4.37 meters per second, times K, which is 2.51 radians per meter, gives us omega is equal to 1098 radians per second. Okay, that's our omega. T is a variable, so then the last thing we're going to have to sort out is what is our phase constant phi. We're going to have to figure that out from our initial conditions. So let's get started on phi. So phi equals. We know that our initial position is 0.8 centimeters. That's when x is 0 and y and t is 0. So let's plug those values into our y equation. Y of 0 and 0 is equal to the amplitude times the cosine of k times 0 plus omega times 0 plus phi. Y of 0 and 0, that was 0.8 centimeters, equals the amplitude, 1 centimeter, times the cosine of 0 plus 0 plus phi. I'm going to divide both sides by 1 centimeter. That's going to give me 0.8. So cosine of phi equals 0.8. That means that phi is equal to the inverse cosine of 0.8. And we have to remember here that the calculator has to be in radians mode. I know I say that a lot, but it's an easy thing to forget and an easy way to introduce a little bit of mistake into your problem. When we hit inverse cosine of 0.8 in our calculator, the calculator tells us 0.644 radians, but that's not the only answer. There is another answer. So if we think about our unit circle, 0.644 radians, that's our answer up in the first quadrant. But 0.644 radians is not the only angle that gives a cosine of 0.8. There's also an answer in the fourth quadrant. That's our angle down here. And this angle is 2 pi minus 0.644, which is equal to 5.64. Okay, so you always have to think of both answers. We have two answers now. We have to pick which one is correct because they can't both be right. To sort out which one is correct, we have to remember that the initial velocity is negative. To use our initial condition that our initial velocity is negative, we'll start with the equation for initial velocity. Velocity is the derivative of the equation for position. When we take the derivative of our equation for y, we get the equation for the transverse velocity, v of x and t, is equal to minus a omega sine kx plus omega t plus phi. Okay, there's the general expression. At x equals 0 and t equals 0, we have minus a omega sine of k times 0, which is 0, plus omega times 0, which is 0, plus phi. Okay, so that's our initial. And what we know is that this initial velocity is negative because that little bit of string is initially moving down. So let's test. So we call this a velocity test. Let's test our two values of phi. If phi is equal to 0.644 radians, then our initial velocity, v of 0 and 0, is minus a omega times sine of 0.644. That's negative. And if phi is equal to 5.64 radians, then vy of 0 and 0 is minus a omega times sine of 5.64. That's a positive value. We know that our initial value is negative, so the positive answer is wrong, the negative answer is correct, and our conclusion is that phi must be 0.644. Okay, now we're all set to finish part A, which is write the equation for y. So y of x and t is a cosine kx plus omega t plus phi. Next, we fill in all of our values. So 1 centimeter, you can put it in meters if you wish, or leave it in centimeters, times cosine of k, 2.51 radians per meter, times x plus omega, 1098 radians per second, times t plus phi, our phase constant, 0.644 radians. So there's part A, our equation for the height of the wave as a function of position and time. Next, we'll do part B. So part B asks for the maximum transverse velocity. Since this is a homework question, why don't we just go through once more how we find that value. So V of x and t is the derivative with respect to time of the equation of y of x and t. Remember the partial derivative symbolized by these curly d's here, di by dt. It means we take the derivative with respect to time, we keep everything else, including x, constant. When we do that derivative, we get minus a omega sine kx plus omega t plus phi. Vy is equal to a maximum if sine of kx plus omega t plus phi equals minus 1. So the biggest sign can never be is positive 1. The smallest is negative 1. Since v is minus a omega times the sine term, if we want v to be the biggest, sine has to be either plus 1 or minus 1. I'm going to choose minus 1 because it gives me a positive value for my maximum. So vy maximum equals plus a omega. So we'll pop in our values. I think at this point I am going to switch to meters. 0.01 meters for our amplitude, 1 centimeter, times omega, which is 1098 radians per second, or seconds to the minus 1, gives me a maximum transverse velocity of 10.98 meters per second. Okay, so that was like a little bit more than we had to do, but hopefully it just brings it home how you're supposed to think about these values. The transverse acceleration, so the acceleration of each of that little bit of string, is the derivative with respect to time. That's our symbol here, di by dt. I'm not sure why you say di. I don't actually remember where that comes from. Of the velocity, which is a function of position and time. We take x as constant, and t is our variable. When we do that derivative, we get minus a omega squared times cosine kx plus omega t plus phi. If we want our ay to be a maximum, that happens again when our cosine term is equal to negative 1. So ay maximum equals a times omega squared. A, I'm going to stick in meters again, times omega squared, gives us a very large acceleration of 12,100 meters per second squared. So the acceleration of that little bit of string is huge. Part C of this problem now is just a plug and chug. Find the initial position, transverse velocity, and transverse acceleration of the wave at x equals 0.625 meters. That means we plug in 0.625 meters for x, and where it says initial, that means we plug in t equals 0. So we want to do that for each of the three values, y, v, and a. So under y, we'll go 1 centimeter times cosine 2.51 radians per meter times x, which is 0.625 meters, plus 1098 radians per second times 0, plus 0.644. Put all that through the calculator, and what we get for our value of y is equal to minus 0.599 centimeters. Okay, I left this guy in centimeters. You can convert to meters if you prefer, but centimeters is fine. Okay, next is V. So we want to plug in minus A. This time I am going to go to meters. Times omega, 1098 radians per second, or seconds to the minus 1, times sine, 2.51 radians per meter, times 0.625 meters, plus 1098 radians per second, times 0, plus 0.644. And what you get when you do that calculation should be minus 8.79 meters per second. Okay, and then last is the acceleration, minus a omega squared, so minus 0.1 meters times 1098 seconds to the minus 1 squared times cosine of k, 2.51, x, 0.625, plus omega, 1098, times t, which is 0, plus phi, which is 0.644, all through the calculator, and what we get is 7,219 meters per second squared. If you wanted to go to 3 sig figs, you'd write 7,220 meters per second squared.